The method for solving second-order differential equations, second-order linear differential equations with constant coefficients, extends pretty easily to higher-order equations. For example, if we should have a third derivative. So here's a third-order linear differential equation having constant coefficients. It's homogeneous. Y triple prime minus 6y double prime plus 11y prime minus 6y equals 0. So in the second order case, what we did is we created a characteristic polynomial by substituting y equals e to the rt. We do the same thing here, and the only difference is that because we have a y triple prime, we're now going to get a cubic characteristic equation. So r to the third minus 6r squared plus 11r minus 6 equals 0. Now, in the second order case, we always could solve this resorting to the quadratic formula if we really had to. In the cubic case, there really is no general formula for the cubic that I can go over right here. So my suggestion would be to solve this either by just graphing or using Wolfram alpha or something like that. I created this example so that there were 3 distinct real roots, 1, 2, and 3. Nothing gets better than that. So that means, just like in the previous setting for the second order equation, our fundamental solution set would be c1 e to the t plus c2 e to the 2t plus c3 e to the 3t. That's all there is to it. But again, we have to solve this cubic. Let's throw on some initial values. In the second order case, we needed to know y of 0 and y prime of 0. In our situation, now we need to know not only y of 0, y prime of 0, but y double prime of 0 as well. So I chose y of 0 to be 0, y prime of 0 to be 0, and y double prime of 0 to be 1. If I plug 0 in here, I get c1 times 1. Remember, the exponentials at 0 will all be 1, so I'll have c1 plus c2 plus c3. That has to add up to 0. Now, if I take the derivative of y, the derivative of e to the t is simply e to the t, so plugging 0 in, I would get c1. When I take the derivative of e to the 2t, I'll get 2 e to the 2t. So when I plug 0 in, I'll have 2c1. When I take the derivative of e to the 3t here, I'll have 3 e to the 3t. Plugging 0 in for t, I would get just 3c3. So you see how I kind of did a derivative calculation kind of in my head and plugged 0 in for t at the same time. So that gives us our second equation. So we have 2 equations so far. Now we need to take the second derivative. Again, the second derivative of e to the t would be e to the t. So if I plug 0 in there, I'd just get c1. If I took the second derivative of e to the 2t, I'd have 4 e to the 2t. Plugging in 0 would give me a 4, so I have 4c2. And similarly, the second derivative of e to the 3t would be 9 e to the 3t, plug 0 in, and you get 9c3. Now we want y of 0 to be 0, y prime of 0 to be 0, y double prime of 0 to be 1. So you can see how we have a system of 3 equations and 3 unknowns. There's different ways to solve this. I would not recommend substitution. If you have taken linear algebra, you could create an augmented matrix and row reduce. But I think perhaps the simplest way would be to use some sort of online solver like Wolfram alpha. You get c1 equals a half, c2 equals minus 1, and c3 equals 1/2. So that means these would be our constants for the initial value problem. Let's take a look at something that's a little bit more challenging. Y triple prime minus y equals 0. So this would lead to a cubic characteristic polynomial r to the third minus 1 equals 0. Now you might think that the only root to this is r equals 1, but there are actually 3 roots in all because it's a cubic. It does indeed factor as r minus 1 times r squared plus r plus 1 equals 0. So one solution would be when r is 1. Another solution would be obtained applying the quadratic formula to this. So we'd have minus b plus or minus b squared, 1 squared, minus 4a, which is 1, times c, which is 1 as well. Again, I'm just looking at this part over here divided by 2. The quantity under the radical is going to simplify to be minus 3. So we'll have the square root of minus 3, which is the square root of 3 times I. What I did was I took minus b plus or minus the square root of minus 3 over 2. I broke it up into 2 fractions, so I had minus 1/2 plus or minus root 3 over 2I. Now, just to go back here, it could very well be the case that you may not remember how to factor the difference of two cubes. I mean, not many students remember how to do that. We don't really stress it too much in algebra these days. So perhaps one way to actually get all three values of r, all three exact values, the one real, which is pretty obvious, and the two complex, would be to simply use an online solver of some sort. So that means we have solutions. R is 1, so that gives us C1 e to the t. That's one solution. And then we need to use these two complex numbers to get our other solution. That's where the cosines and sines come in. So I'll have e to the minus 1/2 t cosine root 3 over 2t. That gets multiplied by an arbitrary constant. And then I have e to the minus 1/2 t times the sine of root 3 over 2t multiplied by an arbitrary constant. So you can see how we used the tools that we learned for second order equations, again in the higher order setting. Now here's a situation where we have a repeated root, y triple prime minus 4y prime plus 5y prime minus 2y equals 0. The characteristic polynomial would be r to the third minus 4r squared plus 5r minus 2 equals 0. Again, you may not see how to factor it. I certainly don't. You use an online solver, you'll see that it has a repeated root of 1 and then another root at 2. So the root at 2 is easy, e to the 2t. We have a repeated root at 1, so one solution is just e to the t. To get the other solution, we have to use the reduction of order method, and that gives us t e to the t. So the repeated root gives us c1 e to the t plus c2t e to the t, and then the 2 gives us e to the 2t. If we had initial values, we could figure out c1, c2, and c3. One thing I should point out that for the third order and higher order, if we switch to the non-homogeneous setting where we have something other than 0 on the right-hand side, it becomes much more difficult to solve, and that's when numeric methods typically are employed.